Hello, I'm Fatemeh from Norwegian University of Science and Technology. I will present ECM, Improving IoT Throughput with Energy-Aware Connection Management. Before we go into detail about how ECM works, let's first take a step back and recap what IoT systems is. In IoT systems, the goal is to capture information about environment or a thing and then transfer it to the back-end system. To accomplish this, we need IoT platforms, which are traditionally battery-powered. But this approach on a large scale leads to high maintenance cost and low sustainability. One alternative is to use energy harvesting technique instead. That means energy is collected from environment to power the system. Example of energy harvesting is solar, vibration, temperature gradients, and wireless transmission. Let's focus on IoT platform. In IoT platform, the heart of IoT platform is system on chip, responsible for collecting samples from environment and transmitting these samples to the backend system. And then we have energy source, for example, solar, energy harvester to convert it to electricity. MPPT stands for Maximum Power Point Tracking. It optimizes energy harvesting by dynamically adjusting the operating point. Without MPPT, the system may not operate at peak efficiency because it helps to extract the maximum available power from energy harvester. Next is energy storage to bridge periods of energy scarcity, for example, during night. And at the end, voltage regulators maximize energy utilization by boosting voltage, enabling more effective use of stored energy. This ensures a stable operation even at low voltage. We investigate state-of-the-art approaches such as Capybara, which use energy-greedy task scheduling. We implemented this scheduler inspired by Capybara. Greedy task schedulers requires measuring the amount of stored energy. One option is to directly measure the instantaneous power output from the harvester, for example by using shunt resistor and ADC converters. Although very low power ADCs are available, their power overhead is at least in the range of several microwatts. Capybara instead uses voltage supervisors to track the voltage of energy storage capacitors at much lower overhead. When the task low power voltage supervisor detects that the platform has stored sufficient energy to execute it successfully, a scheduler which runs on the SoC dispatches the next task. We discovered that IoT system throughput is closely tied to how the system addresses management tasks, including connecting to the backend system or transmitting packets to keep the connection alive. Let's illustrate this with an example. In this plot, x-axis represents time, y-axis power consumption, and this example varies different tasks. Schedulers wait until the system has harvested sufficient energy to connect and transmit sample data and then disconnect. By looking at the energy breakdown, we see a little bit energy consumed on sampling and transmitting, much more on connecting, and the rest is asleep. How about if we have more data needs to be sent to the back-end system? Now we spend most of the energy on connecting that could have been used to collect or communicate sample data that is clearly suboptimal. The another option is maintain connection MC policy. Connect one time to the back-end system and aims to keep the connection alive continuously and sample and transmit while keeping the connection alive. By looking at the energy breakdown, we see much more energy spent on sampling and transmitting Also, we have keep alive packets and one-time connecting. How about if we don't have much data needs to be sent to the backend system? Now, energy consumption is dominated by keep alive packets, and it would be better to connect and disconnect. We proposed Energy-Aware Connection Management, ECM, which uses a lightweight analytical model to decide if the connection should be maintained or not. And if it decides to maintain the connection, ECM tunes the sampling period. Let's use this simplified example to explain ECM. In these figures, the x-axis represents time. The top figure displays harvester power on the y-axis, while the bottom figure shows consumed power on the y-axis. When the harvester power is low, ECM adapts the on-demand connect strategy. With medium harvester power, ECM decides to maintain the connection with sampling period of Ts. By increasing harvester power, ECM decreases the sampling time and sample and transmit more frequently. Increasing the harvester power further results in a more reduction in the sampling period, ultimately causing the disappearance of keep alive packets. As we get higher power, productive activity is increasing. In all these examples, ECM minimizes the number of management tasks by configuring the suitable connection strategy and tuning the sampling period. This plot exemplifies the main operation of ECM. In x-axis we have time and y-axis represent stored energy in the system. We focus on the energy threshold ET0 and ET1, which signify that the device has stored sufficient energy to execute task T0 and task T1. The energy harvesting subsystem interrupts the SOC when an energy threshold is crossed. At 1, the amount of stored energy crosses the threshold ET0. ECM starts a timer. At 2, the stored energy exceeds the communication task threshold ET1. ECM inspects the timer and measures the amount of time delta T that has passed since crossing ET0. Since ET1 and ET0 are known, we know how much energy the system gained or lost across delta T. We know the net charge and we know how long it took and we know what the application did in meantime. We can also predict how much energy it spent, and this enables us to compute average harvesting power, pH. And then we should try to adapt sampling periods such that we balance energy harvesting and energy consumption. This is the equation we can predict Ts. ECS star is work proportional energy. If you do more work, for example, sample more frequency, ECS star increases. pH average is average harvesting power that we predict from previous slide. And PCS star average is time proportional power. It's about things are increased with time. If you decide you want to be in idle mode longer, PCS star increases. ECS star and PCS star are determined at design time. If PCS star is greater than pH average, TS is negative, which indicates that the harvester power output is inefficient to maintain the connection. In this case, ECM adapts an on-demand connect strategy. Otherwise, TS is positive, and ECM attempts to maintain the connection with sampling period of at most TS. ECM recomputes this equation every time a threshold is crossed after connecting to the backend system and updates TS according to the harvester output power. In this plot, x-axis represents average harvester power and y-axis throughput in byte per second. For our Proto-NN benchmark, we can compare throughput with OC, MC, and ECM across our outdoor solar panel configuration. Throughput increases with energy. To easier compare the connection managers, we can add a plot to show throughput normalized to MC with each solar panel. These figures demonstrate that when the average harvester power is low, OC, MC, and ECM operate similarly and connect on demand. For solar panels with moderate output power, ECM substantially improves throughput over OC and MC. OC yields low throughput because it is too conservative. It disconnects from back-end system even the system has sufficient energy to transmit more samples. MC, on the other hand, is too aggressive and causes the system to run out of energy because it sample and transmit too frequently to be sustainable. ECM achieves the best of both worlds by using its analytical model to select a favorable connection strategy and sampling period. To demonstrate why ECM outperforms OC and MC, we break down energy consumption of Proto-NN benchmark with the 117 microwatt solar panel for OC, MC, and ECM connection strategies. We break down energy consumption into active time in idle and deep sleep low power mode, idle sleep, deep sleep, checkpointing, storing application state to non-volatile memory, and restoring the state once sufficient energy is available, and capturing and processing samples, sampling, keeping the connection alive, keep alive, transferring packets to the backend system, transfer, and connecting refers to the connecting to the backend system. And at the end, unused represent the remaining energy in the system at the end of experiment. This figure demonstrates that ECM outperforms OC and MC because it spends more of the available energy on collecting samples and transferring samples to the backend system. In other words, the sampling and transfer categories are significantly larger for ECM than they are for OC and MC. ECM successfully keep the connection alive and hence spent less energy in connecting categories compared to OC and MC. This comes at the cost of ECM spending more energy in keep alive category. But this is favorable because keep alive packets overall require much less energy than reconnecting. To conclude, ECM employs analytical modeling to efficiently manage connections and adapt sampling periods to balance energy supply and demand. ECM operates near the energy inequality point, thereby reducing the need for management tasks and ultimately improving throughput. ECM improves throughput by up to 9.5 times and 3 times compared to the on-demand connect and maintain connection policies, respectively. Thank you for watching. I hope to see you at the conference.